Okay, morning students. Hope you are able to hear me. Yeah, okay. Welcome to this digital design course. Uh, I'll be the instructor in charge for this course, and Ankur Bhattacharya, he will handle an L2 class. Okay, so this is going to be an online mode of class, right? As you all know. We'll see how various classes are going to be held. Lecture classes, it's going to be purely as per timetable through Google Meet. Okay. The presentations, you don't have to note down anything because the presentation, as soon as the lecture is over, I will upload the presentation. Okay, onto the link is already given to you. I have published a link in the CMS, right? So in the CMS and in the study materials for digital design, okay, this link is there. You can actually log into my webpage, which is sanjayvidyadharan.in, and then you will have various tabs. So in the download tabs, you'll have all the study materials for this course. Okay, so I will upload this presentation in PDF form also there, right? And also in the video lectures also, I'll be uploading whatever is been taught here or spoken here is going to be recorded, and I'm going to upload this video also there. Okay, so you don't have to note down anything, just keep listening to carefully to what is being told in the class. Okay, the tutorial class, again, the concept is that I'll be uploading the tutorial onto the on the link provided. Okay, a week ahead of the class. Like already I have uploaded the tutorial one, right? So the theory for that will be discussed probably on the next class, but and you will have to attempt those problems this week. Okay, next week tutorials, the solutions will be discussed by the instructors in the respective tutorial classes, right? So you have to somehow find time, try to solve the questions yourself based on the theory which is discussed in the class. Okay, if you don't do that, then you may not appreciate the concepts very well. So right, so it is better that you try to at least attempt the course once. Okay, so the silent features of this in the lab, it is going to be a slightly different one, right? I am going to provide links for the videos in which the entire procedure to be followed to carry out the experiments will be explained in those videos. Also, the problem statement will also will be given. So for the first three labs, we are going to have it in LT Spice. Okay, so in the link on how to download LT Spice, how to install the various components of LT Spice, I have already published that. I have given the link to all. So this week you are going to, in this week you are going to download, go through that video, download the material, the entire material, the LT Spice software onto your laptops, and you need to do the experiment yourself at your own time. Okay, so that video is pretty exhaustive. I don't foresee you getting into any problem. In case you are getting stuck anywhere, okay, feel free to call me up, mail me, and it will be ideal if you have a team viewer so that I can come on to TeamViewer and resolve your problems, or you can even get in touch with your respective lab instructors. Okay, anytime between 8 to 12 in the night, you are free to call me up and resolve any problems whatsoever you have. Right. So the first 3 weeks we are going to have it on LT Spice. Subsequently, we will move on to Verilog on ISE. Again, I'll brief you that later on. Okay. Time being, you all just download the first video, go through the video, and as has been explained in the video, carry out lab experiment 1. So in case you have any problems during this week in your lab, you can get in touch with your instructors. Next week onwards, whatever work you do, right, you have to be, you will be evaluated, right? So there will be 4 marks per lab. So in Google Meet, you will display your schematic. The instructor will ask you to show you the schematic, and he will ask you to run the simulations, and he might ask you 1 or 2 questions to verify if you have done it yourself. So don't try to copy from here and there your friends files and try to show that. Okay, so these are all very simple experiments which you can do it yourself. So try it, and you have adequate time also, right? You will have one full week to do your experiments. So do it sincerely, and then you give a viva and upload your files in the folder which will be given by your lab instructors. Is there any doubts? You're free to come on, switch on your mic and ask any doubts if you have. I'm recording this video. I'll share this with everybody, right? In the link provided, I'll keep uploading all the videos, right? Okay. Tutorials are not going to be evaluative. Okay. Tutorials are going to be only, and you just have to do the tutorials yourself, and the solutions will be discussed in the tutorial class, and that's it. And lab every week you are going to be evaluated, right? Okay. First lab is this week. It is not going to be evaluated. This week I have given only lab. I have given the problem statement for the next week. So this week you are supposed to download the video, install LT-Spice, and carry out experiment one. Okay, from Monday to Saturday you have time. Next Monday onwards, your evaluation for the lab starts. Okay, next Monday I will upload the experiment for the next lab. Okay. So that is the scheme of things which we are going to follow for the lab. Okay. So all the notices will be on CMS. Over and above that, I'll put all the notices in Google Classroom also. So I'll recommend all of you to join this Google Classroom. Okay. Lecture 2 will have a different classroom. You can go to that classroom to attend the classes, but nevertheless, you will use this ID to join the so that you get notifications. Okay, all the links will be available here, all the notices and the study material will be posted here. It will be there in CMS also, but nevertheless you can join this. Okay, so my mail ID is flashed here, my phone number and WhatsApp number is flashed here. Okay, so feel free to contact me any time. Okay, so so let me introduce myself now before I move on to the next slide. Okay, I am Dr. Sanjay Vidyadharan, right? Retired as a wing commander from Air Force. I completed my B 1994 from NIT Bhopal. Okay, and then I joined Air Force in 1994 itself. And 2008 to 10, I took 2 years of study leave from Air Force, and I did my master's in VLSI design, microelectronics and VLSI design from IIT Kharagpur. And then I went back to my parent organization, Air Force, and I worked till 2016. So after having spent 22 years with Air Force, so I thought, okay, let me switch over to some other, do a second innings in academics. So I am passionate about teaching, so that's why I came to this. Then 2017 to 20, I finished my PhD in this institute itself, BITS, at BITS itself. And once I finished my PhD, the department felt I am good enough, and they gave me a position of faculty here itself. So that's how I'm continuing here as a faculty. Okay, that's all. So I have a son who is in BE final year SRM, Chennai. He just finished his BE, and that's all. The small family with one wife and one son. Okay, that's all about me. Okay, these are the textbooks which we are going to follow. I have uploaded the soft copy of all these books, the Google link, which I have provided to you. Okay, so if you don't want to buy a hard copy, you can download the soft copies from the study material. Okay, there is an ebook folder also, so you can download these books from there. Then these are the course content. I have already shared with you the Google Classroom ID, right? I have the course handout I have already shared with you, so you can go through that, right? Okay. This is going to be the evaluation pattern. There are going to be three tests, T1, T2, T3. It will be 30 minutes duration, okay, of 30 marks. It will be of 30 marks. So the total marks is 200. So you can multiply into 2 the weightage given. Okay. So T1, T2, T3 will be in Google form or something like that. Okay, but there'll be very little scope of cheating and all, because Let me tell you, I mean, each one of you might get a different question randomly, right? I'll make a huge question bank. So you might as well put in a little bit of effort and prepare well for these exams. Okay. Regular lab evaluation, I told it's of 20 percentage. So it will be around 40 marks. Each lab will be of 4 marks. So at least 10 labs you will do in this session. Okay. So final lab exam could be another, it could be quiz or it could be even practicals. Okay, that mode of examination will convey to you, subsequently towards the end of the course. Similarly, there will be a comprehensive exam which will be decided by the timetable division. Okay, that also they will do it. Right. Okay, now coming to digital systems. Okay, there are two binary logic states, right? Okay, that is the difference between an analog and a digital system, right? Okay, so don't try to note down thing. I'll share the PDF as well as the video. Okay, so there are two binary in binary in digital systems. Digital system could be binary, ternary, or something like that. So conventionally, it is a binary system where there are only two levels, zero or one. Unlike an analog system where you can have infinite, the signal can take infinite levels. It could be 0.1 volt or it could be 0.10001 volt also. So in binary logic states, the signal can take only two levels. It could be zero or it could be one, right? And that is not fixed, okay? Depending on the hardware, okay, what is corresponding to zero, what is corresponding to one will change, right? There are two different voltage levels. Like in the lab, we are going to use TTL gates. Okay, TTL gates TTL stands for transistor logic, and it's an very old technology, but still very much used for discrete digital ICs. Okay, so it is 0 and 5 volt. Okay, whereas in CMOS technology, in the microprocessors and all, so earlier microprocessors, they were all working on CMOS 180 nanometer. Okay, what does 180 signify? It is the minimum size of an unit device. Okay, the unit device is an NMOS or a PMOS. Okay, and the minimum size is going to be 180 nanometer. You can have in circuits devices which are more than 180 nanometer also, but the channel length, minimum channel length you can design is 180 nanometer. So that is why it is known as 180 nanometer, right? So then the technology as it evolved from 180, it went to 90 to 45 nanometer to 7 nanometer. Presently, the most of the chips which is coming out in 2020, whatever has come, right, is 7 nanometer chips. Okay, 7 nanometer chips, what does it mean? The smallest device, okay, NMOS or PMOS has got a channel length of only 7 nanometer. Okay, so you can have high packing density, it will be faster. So if you have small devices, they will work faster and they will have lesser power and has got great advantages that we will see towards the end of the course. By the time you will get exposed to little bit of microelectronics also, then I will tell you what are the advantages of various families and things like that. Okay, time being, I'm just wanted to tell you that depending on the various hardware requirement, 0 and 1 could be different value. Okay, in the lab, whenever you do the simulations, please ensure you give signal wherever you want to give one signal, give 5 volt, don't give 1 volt. Okay, it will not work because it is TTL gate, and 1 will be taken as 0 in a TTL logic. Okay, and you have to give 5 volt to be considered as 1 volt. So in the lab, just ensure when you're doing experiments in the LT spice, wherever voltage is to be given as 1, give 5 volt. Okay, just keep that in mind. Okay, now what are the advantages of a digital system? Okay, what are the advantages? See, analog system, when you transmit from place A to place B, it will pick up a lot of noise, right? Any signal will pick up, because how do you transmit signals? Either through a wire or through a optical link or through RF. So in all these modes of communication, there will be noises. Also, when you receive a signal, it has to go through an front-end amplifier. All these electronic components also will add noise into the signal. Okay, because of heat and things like that, these components, and there will be some noise. Okay, so you will find, okay, Once you amplify it in an analog signal, even the noise will get amplified. There is no way you can eliminate the noise, because the frequency of the noise and the frequency of the audio signal, what is their audio or whatever is the data signal, you can't distinguish between them. If you try to delete some signal, your data also might get deleted. So there is no way you can segregate a noise from this signal. Okay. Whereas in a digital system, see, you see a square wave, which is being transmitted, it will pick up noise. Okay. So in the receiver end, what do I have to do? I have to just set a threshold, any voltage. Say for a 5 volt system, I will set any voltage which is coming beyond 2.5, I will take it as 1. Any voltage which is coming below 2.4, I'll set it 0. So all noise will get eliminated, right? I just have to set a threshold. So anything above the threshold will become 1, anything below the threshold. So the noise can be eliminated. In fact, you can have, if you are transmitting the signal for a long distance, you can have repeaters at regular intervals. Like if you are having one tower which is transmitting for certain, and you have to transmit a signal for 100 kilometers, every say 20 kilometers you put a tower, it will receive a digital signal, right? Regenerate it. You set a threshold and you generate. So all the noise will get then removed, and then you retransmit it. Okay, so that is why you are. So in case you are not following anything, feel free to switch on your mic and me and ask me question, or you can put it in the chat box also, right? No issues with me. Okay. Now, what are the other advantages? Okay, the other advantages is, like, most of the microprocessors are based on digital. Okay, and you don't have analog microprocessors, so microprocessors and all are easy. So computation is easy when you have a digital system. The computation becomes easy because you have a lot of digital systems, which can do your computation. Okay, storage and retrieval of data, right? See, it is very easy to store a 0 volt or a 1 volt, right? So you can have a flip flop, a small storage cell, which can, a switch, like a switch is also can be 0 or 1. Like, so you can have a mechanical switch or an electrical switch or an electronic switch, which is easy, 0 or 1. So you can store data, right? But if you have an analog signal, you will require so infinite number of levels to store the data. So storage and retrieval of data is very easy. Okay. Then error detection and correction is possible. Okay, this we'll see in the lab also. See, what is error detection? Suppose I have a 4-bit data to be transmitted in between me and say Manish S. Patel, right? We are transmitting C data. So if at all I have say I can have an error detection. Like I will say, okay, Manish, I will send you, instead of 4 bits, I will send you 5 bits. Okay, if I send the 5 bit, in the fifth bit, I will do some encoding in such a manner so that in total 5 bits there will be only odd number of ones. Okay, so if say if I have to transmit 1000, then I will add 1000. The fifth bit will be 0, so that the total is 0. So that is known as an odd parity. Okay, I'll send it to Manish. So Manish, once he receives the signal, he will see that, okay, there are 5 bit, fifth one is my error detection code, and he will see that it is total is odd number. That means there is no. Suppose during the transmission, one of the signals gets transmitted wrongly and 0 becomes 1, then Manish will come to know, because now he will get 5 ones, right, 2 ones. So it is odd, right? So he'll come to know, okay, some error has happened. So if there are more than one errors which gets introduced, then he will not be able to detect it. Okay, so that is known as error detection, right? What is error detection? You have one additional code, and then the receiver will be able to detect. So those kind of codes are possible only in digital. Similarly, if you have few more codes added, you will learn those algorithms. Mostly the computer students and so computer science students will learn in your advanced courses, that even the correction is possible, right? So it will be always, so nothing comes free in life. Okay, so if you have to do error detection, you require one additional bit. You, okay, instead of 4 bit, now I have to transmit 5 bit. That means more bandwidth it will take. Similarly, if you have to do correction, you might have to, instead of 4 bits, you might have to transmit 6 or 7, so that there will be you can do the correction also. So those kind of things are available. These are just don't try to understand everything here. Just keep in the back of the mind, okay, these things are not directly related with your exam. This is just an introduction to the digital systems. Okay. Now, digital signal processing enables wide variety of applications. What does this mean? Like in earlier days, so if I had a signal and I had to pass it through a low pass filter, I had to make a low pass filter using an a resistance and a capacitance. Okay, to remove that frequencies, because sometimes say if I transmit a signal, a voice signal, okay, because of power supply variations also sometimes it gets the power supply, because you are passing that signal through an amplifier. Okay, so what is the power supply given is the 50 hertz signal. So sometimes that 50 hertz noise also gets coupled to the signal, right? So whereas my voice signal, I will have most of my voice signals will be from 1 kilohertz to 3 kilohertz. In that bandwidth will be the maximum voice content. So if I when I transmit my signal, I will find that 1 kilohertz along with that my voice signal there is some noise, power supply noise and all, which is transmitted. At the receiving end, what I will do generally in earlier days, I used to have a high pass filter, an RC, a resistance capacitance filter, which filters out this 50 hertz, so that noise is eliminated. Okay, now so there are various ways you can do signal processing. So they were all done in hardware. Okay, in the earlier days. Now in digital signal processing, once you get the digital data, in the digital you can make digital filters. Okay, with the data itself that you will learn in your digital signal processing classes, how you can from a given data stream, how can you eliminate one particular frequency, and how can you boost your image, and a lot of things can be done. How can you mix two signals? So all those digital signal processing is possible these days with digital signal processors. That's why digital systems have become important. Okay, the last one is again an important, encrypting and decrypting. Right, analog signal, it's very difficult to encrypt. Even if you try to encrypt, it will be easy to decrypt them. Okay, whereas in digital systems, say you have a string of data which is to be transmitted. Okay, you are transmitting a data. How do we generally encrypt? Okay, suppose I have a data 10101010 and some data going, I will mix up another series. Okay, say 01, it will not be a square wave kind of thing. It will be a random series. Okay, it is known as, it's not purely random, it will be pseudo random. Okay, it will be like 110011121110. Okay, some series. So I'm going to mix this up with my signal, with the actual data, mix these two signals and encrypt the data. At the receiving end also, if my receiver knows with what random series I have mixed up, he also has to know the same series. Okay, so he will also employ the same technique to decrypt it. So unless the transmitter and receiver they know the code, the third person cannot decrypt it. So encrypting, decrypting in a digital system is very easy. And once you encrypt it, it is literally impossible to decrypt it. Okay, digital systems very difficult to. Okay, so that are the advantages of the digital system. Okay, another advantage of a digital system is time division multiplexing. Okay, what is time division multiplexing? Like I have a voice signal. Okay, my voice signal is maximum 4 kilohertz. So there is something known as Nyquist criteria. If I sample my voice signals at 8 kilohertz and send only those samples at the receiver end, I will be able to decode them. Okay, I will be able to get the exact, I don't have to send the entire signal. Okay, that also you will learn your communication classes. Okay, whatever if I am speaking at 4 kilohertz, maximum my voice can have up to 4 kilohertz. So if I sample at 8 kilohertz, okay, and if I send only those samples also, I'll be able to construct, the receiver will be able to get my voice signal exactly the way I have transmitted only with those samples. Okay, so when I take the samples, I'm taking at 8 kilohertz. So there will be a lot of time available in between those two samples. So in those time intervals, I can take other signals also. Okay, that is known as time division multiplexing. Okay, time division multiplexing is possible in a digital system because you are transmitting short pulses. In between that period, some other signals also can be transmitted. So if I have a mobile tower close by here, not that all of you, or each one of you will be assigned a separate frequency. Okay, okay, Vedant, you take no, one say 50 megahertz signal. Okay, Bola Shri, you take some signal of 52 megahertz, and Swapnil I gives one more frequency. It's not going to. I mean, so you will require, if there are so many of you together, I'll require such a big bandwidth. It's done like that. Okay, so each one of you will it is like time division. The same frequency will be used by n number of people. Only thing is they will all be given that particular slot to transmit the signal at a particular time division, right? And the switching happens at high frequency that you don't come to know that okay, many of you are using the same frequency slot. So those kind of advantages are there in digital systems. Okay. Okay. Now, one of the disadvantages is of the digital system is it requires a large bandwidth. Okay. Excuse me. See, a square wave. Okay, this is again part of control signal systems, which you will learn. A square wave of 1 gigahertz is actually, speaking, okay, it is a summation of sinusoidal 1 gigahertz, sinusoidal 3 gigahertz, sinusoidal 5 gigahertz, like that, right? It contains, that is known as Fourier series. A square wave is actually can be split into, okay, fundamental frequency is 1 gig. Suppose the square wave fundamental frequency is 1 gigahertz, it can be split into infinite number of sinusoidal signals in the multiples of the fundamental frequency, right? So it might have a sinusoidal signal of 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz, and but the magnitude of each of these signals will be different. Okay, so on the right hand side, if you see a graph I have shown here, there is one signal. Okay, the fundamental frequency will have the maximum amplitude, then the higher harmonics, they are known as the higher harmonics, will have lesser amplitudes. Okay, so if I have to transmit a pure square wave, what is the bandwidth required? It will be infinite. Okay, understood? To transmit a square wave, okay, square wave is made up of sinusoidal signals, right, in the multiples of its fundamental frequency. So to transmit a perfect square wave, I require infinite bandwidth. But the generally, so that is the disadvantage of, generally infinite bandwidth is not given to a digital system. A finite bandwidth will be given. So the fundamental frequency will be transmitted, and maybe 10 or 20 higher frequencies also will be higher harmonics also will be transmitted. So what you receive will be something which is shown here. See, it is not a perfect square wave, right? You will get something like this. Okay, so this distortion will happen at the receiver end. Okay, because you are not having an infinite bandwidth. Okay, but once you receive these kind of signals, you can, all that you need to do is set a level for deciding whether it is 0 or 1, right? So easily you can detect whether it is a 0 or 1 by setting an appropriate threshold voltage. If I set a threshold voltage in between, so these small variations also, this is also kind of noise. This, you can term it as a noise induced by bandwidth limitation. Okay, if I call it like that. Okay, you can do that also, right? So this is the disadvantage of a digital system, right? Another disadvantage is everything in the real world is analog, right? And it is an so you will require ADC and DAC. In real life you cannot have right, you cannot have an pure digital. Then everything will look black and white. There will be no colors in life, right? So if you see, Ayush will find everything black and white. He's feeling things are cool because the life is colorful, right? Okay, so that is the required. So in life, it's everything is analog in the real life, in the real world. Okay, that is why it's so colorful, right? So that is why you will require A to D and analog to digital conversion and digital to analog conversion, because finally it is the human being, right? The signals are produced by the human beings, and it is to be finally given back to the human room in the as in the form of an visual signal or optical signal or audio signal or whatever it is, and heat, whatever it may be. The final output is always analog, and the initial input also will be initial. Okay. Then see the long distance transmission by how do you transmit data from place A to place B? There are various modes. Okay, it could be RF signals, right? Radio frequencies through towers, or it could be through a wire. Okay, through a wire you can transmit a signal, or it could be through an optical link. Okay, all these signals, right? When you transmit from place A to place B, it is possible only you can't transmit just plus 5 volt or minus 5 volt, right? Or a 0 volt, right? RF doesn't work. It requires an analog signal. So all this, even in wire also, if you try to transmit plus 5 and minus 5, there will be a lot of leakage and dissipation, and you won't get the correct signals. It is always better to transmit analog signals. Okay, so you have to do modulation. Okay, so for a simple wire, like you have a modem and all, right? Okay, so what does the modem do? For one, it transmits, say, one frequency, 1 kilohertz, and for zero, it transmits another frequency, 2 kilohertz or something, right? So you generally you have phones, which when you dial, you hear that tone two, right? What is that? They're all tones which are transmitted. That is analog signal is transmitted. For zero, you have one tone, and for one, it is transmitted one tone. So that is the disadvantage of a digital system, that you can't find transmission from place A to place B has to happen only in analog mode. Okay, within the chip, within the laptop, within a PCB, no, it is always digital. Okay, whenever long distance. Okay, so the key here is long distance. Okay, even for short distance from place A to place B, you can have digital within your room or something like. Okay, so these things. Okay, so that is it. But even when you are Bluetooth or Wi-Fi, okay, it doesn't transmit the digital. It will transmit analog signals. Okay, some frequency for zero and some other frequency for one. Okay, so that is the disadvantages. Okay, now let's have a look of some of the very basic binary logic gates, S gates. Okay, S A. If you give zero, then output will be zero. If you give one, it will be output will be one. So is this foolish gate? No, it does nothing, right? It's not a foolish gate. Okay, so generally these are known as buffers. Okay, so whenever you have a processor which is doing some process, no, doing computation, and it is giving an output. Now that output you might have to transmit to a different IC, to a different PC. So you can use a buffer which will isolate the input and output. Okay, it will amplify. It will not amplify. It will ensure that the output currents are provided from the power supply through the buffer, and the input, whatever you have a computational device, that is not getting loaded. Okay, so it isolates output and input. So this is also an important gate which we generally use for as a buffer. It's known as a buffer. Okay. Similarly, you have a NOT gate. NOT gate is what? It just in 0 to 1, 1 to 0. Okay. So this is the logic representation. Like different families, it will be different. For a TTL gate, okay, 1 means 5 volt. Okay. For a CMOS 45 nanometer, 1 means 1 volt. Okay. So this is only logical expressions. Okay. Logical states 0 and 1. Right. Okay. Similarly, you have and as the name implies, okay, only when both A and B are 1, the output will be 1, whereas if any one of them is, it is 0. Okay, so this is an AND gate. Okay, so similarly you have an OR gate. Okay, so OR gate is nothing but, okay, even if one of them is 1, the output will be 1. Okay, and the third important gate is XOR gate. XOR gate means it is different from the OR gate, because if both are 1, it will be 0 here. Okay, it will be give an output only when one of them is 1 and other is 0. okay, for the other. So these are the it's known as these tables are known as the truth tables. Okay, truth tables for the gates. These are the symbols of the gates. Okay, these are all standard symbols, and these are the associated truth tables, binary logic. Okay, okay, this is NAND. Okay, you might be wondering, why do you require NAND? And is a more easier gate. Okay, it, NAND and NOR are very very important because finally these gates, okay, whatever you might write a code, finally it has to be implemented in hardware, right? So finally some voltages requires some, you will have to make some circuitry which will take inputs and give outputs, right? So when you implement a gate, it is not possible to implement AND gate. Okay, that is a positive. It's not as a positive gate. Okay, you can't implement a positive gate, circuit wise. You can always implement only a NAND gate very easily. Similarly, you can implement a NOR gate very easily. And if you have to make an AND gate, okay, you have to make a NAND gate and invert again, use a one inverter to get an AND gate. Okay, so that when we read about the circuits towards the end of the course, I'm going to cover the how this NAND gate functions internally, because you have not yet done the microelectronics course. So once you do that, I'll towards the end of the course, and we will dedicate few classes and understand how these gates internally, how they are going. Okay, just understand that to synthesize an AND gate, it is always a NAND gate followed by an inverter, right? And a NAND gate can also be it's known as a universal gate. You with NAND gate and synthesize any logical function. That also towards the in the next few classes you will understand. So that NAND and NOR are known as the universal gates. Okay, if you have to configure a NAND gate and inverter, you just have to short both the inputs. Okay, and give A. So if you see the truth table, this will work like an inverter. If you short these two inputs and give one input here, okay. If you give 0, 0, 0, it will be 1, and if you give 1, it will be 1, 1, it will be 0. So these are universal gates. Okay. Now I'm just putting this slide to give you a brief idea about how we came to this state-of-art 7 nanometer device. The first logic circuits which was implemented was diode transistor logic. It used a diode and a transistor. And in 1990, this was a PCB based design, okay, in discrete components, okay. Then in 1961, we came to resistor transistor logic, right? It used a resistor and a few transistors, and it was again this was based on PCC. Then came TTL logics. Okay, in this TTL logics, all the 74 series lab experiments we are doing, all the ICs they have TTL logics. Okay, in TTL logics there are few transistors and discrete ICs. Okay, now each of these logic circuits I told towards the end of the course I'll explain you and what were the advantages of these logic gates, and although they are outdated, but there is a lot of learning value if you try to understand how these logic gates function, which towards the end of the course I will explain. Okay, then we had emitter coupled logic. These four were bijunction transistor based, BJT based. Okay, first microprocessor was based on emitter coupled logic 3C, was 360. Then came 460, 560, and all. So they were all BJT based. Then CMOS, this was the first CMOS based, complementary MOSFET based. It consumes very less power. You have high packing density. So since 1974, it is the CMOS technology, which is working till. Okay, so the first chip had 2000 transistors, Intel 4 then, and the minimum device size was 10 micrometer. As of now, the device has become so small, 7 nanometer, right? You can't even see from your naked eye, and it is in a nanometer scale device, right? So you have billions of transistors in the in one IC. Okay, this is how the evolution has taken place, right? Okay, now noise. Let's see some of the common terminologies which are used in the digital system. Okay, first is the noise margin. See, in the TTL gate, what you are going to use in your lab, okay, from anything between 2 volt to 5 volt, the chip will take it as logical 1. Okay, where does these values come from? That once you understand the circuit, you'll be able to appreciate where this has come. Okay, time being, I'm just telling you, okay, 2 to 5 volt, it will take it as logic 1, and 0 to 0.8 volt, it will take it as logic 0. At the output, for logic 0, the minimum voltage it would give is 2.5 volt to 5 volt, depending on chip to chip fabrication. Okay, so the minimum voltage it will give is 2.5 volt and maximum is 5 volt. Similarly, maximum for 0 it will go, maximum voltage can go up to zero point 0.4 volt. Okay, you might say, why is this band? Okay, because see, when you fabricate a chip, not every chip is going to give you perfect 5 volt. Okay, so there is a band, so the output voltage can be from 2.4 to 5 volt, anything the manufacturer says. Okay, and why this variation also, once you understand the circuit, then you will come to know. Time being, just note down that, okay, the output voltage can be, now if you see, this output is going to drive the next stage, right? It will be through a wire or PCB, whatever connection. So how much of noise can our circuit tolerate? This is 2.4. So if some noise comes in, it can again further come down till what? Till 2 volt, because till 2 volt the next stage will take it as logic 1. So this difference 2.4 to 2 volt is known as the noise margin high. Okay, similarly, the maximum for a 0, I can maximum transmit, and the output which will be available will be 0 0.1. Now I am transmitting this signal to the next chip. In the next chip, till 0.4 volt I will take it, and it will accept as 0, right? So what is the maximum noise which can get into the system, which can be tolerated, is 0.04 to another zero point 0.4 volt of noise also, doesn't matter. Okay, it will still accept it as 0. Anything noise more than zero point 0.4 volt, this will go beyond 0.48 volt. Okay, but in the forbidden Bhagavan Barose band, so you should not do that. So this is where the noise margin definitions come. Okay, this is zero point 0.4 volt, zero point 0.4 volt. Okay, this will be again specific to circuit from system to system. For 4 series of ICs which we are going to use in the lab, this is the noise margin levels. Okay, the next one is propagation delay. So when you give an input signal, say this is an inverter, you give an 0 1 0, output will be 1 0 1. All right, so it is not that you give a signal immediately the output will be 1. Okay, because there will be some node capacitance, they will get charged slowly, they will get discharged slowly. So this is again from circuit to circuit, it will different. Okay, so this is one terminology which we generally use, is the propagation delay high to low, right? When the signal is going from high to low, okay, this input signal, the time it has reached 50% till the time the output has reached 50%. So this T1 minus T0 is known as the propagation delay. Similarly, here the signal has gone low at T2. Okay, so 50%. Whenever the input gone to 50%, that is reflected as T2 here. When the output has reached 50%, T3. So T3 minus T2 is known as the propagation delay. Okay, low to high. Okay, so this is the propagation delay. Okay, common terminologies other is rise time and fall time. Rise time is when the time taken for the signal from 90% to 10%, and similarly that the fall time. Rise time is from 10% to 90%. Okay, this also depends from circuit to circuit, logic family to family, they are all different. Okay, I'm just introducing you to some terms. Okay, and then last one is power. Okay, so there will be there are many kinds of powers in an IC, a digital system. One is known as static power. Static power means whenever the input is not changing, right? But still there will be some power which will be consumed. Even if you have not given input, even the output is remaining stable, still there will be some leakage power. That is known as the static power. Okay. Dynamic power is whenever the input is changing from low to high or high to low. So there are several types of dynamic power. Okay, so these also we will learn towards the end of the course. I'm just introducing to some terminologies right now as an introduction. Okay, so that's all for today. Anybody has got any doubts whatsoever, and feel free to ask me. Okay. Noise margin. Okay. This is my IC. Okay, 740s. One gate. So it's a one gate. This gate, it any input voltage which I give between 0 to zero point 0.8 volt, it will consider it as 0. Okay, any voltage will give between 2 volt to 5 volt, it will consider it as logic 1, and accordingly do the computation and give you an output. Is this much clear? Okay. Okay, Manish, what so input I need not give 0. Even if I give 0.5 volt also, it will take it as 0, right? Similarly, if I give 3 volt input also to this gate, it will take it as 1. But if I give some voltage, say 1 volt, okay, then the manufacturer will say, okay, output you made anything. I am not responsible for that. Okay, similar. Okay, now this is the gate. Now the when you give within this band, okay, if I give no, within this band, the output will be within this bands. Okay, output will be for a logic 0, 0 to zero point 0.4 volt for logic 0, 2.5 to 5 volt for logic 1. That depends on the gate, right? If it is an inverter, if I give any voltage, if I talk about an inverter, if I give any voltage 0 to zero point 0.8 volt, the output will be anything between 2.5 to 5 volt. And if I give any voltage between 0 to 5 volt, the output will be anything between 0 to zero point 0.4 volt. Is it okay? Yeah. This is a NOT gate. It could be a NAND gate also, anything. For a NAND gate also, and depending on two kind of input signals, if the input signals are within this band, within this blue band, the output will be also within this blue band. That's what the manufacturer will assure you. Okay, so it could be NAND gate, be any gate. Okay, so the output will be within this band. If you give inputs within blue band, you will get outputs within blue band. Okay, now why I call this noise margin is, now this output I write another gate, right? It could be within that chip, it could be on the PCB on a different chip, right? On a different chip. So when I transmit, it will pick up some noise. That wire will pick up some noise, right? Somewhere. So how much noise can my circuit tolerate, right? It is 0.4 volt, right, minimum. So this, so it can maximum another zero point 0.4 noise also gets added. The next stage, there will be no error induced, right? Is it clear now? Okay, so that is how these noise margins are defined. Okay, anybody else? For NMH, VOH minimum, that is 2.4 volt. Yeah, it will be VIH. Correct. Correct. Yeah. Sri Harish, I couldn't understand the this thing. What is the difference between two gates? What is the one? What's your question like? Okay, I guess he might have. Okay, that's all for today. Yeah, yeah. Tell me. Uh, No, 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 no. It is like for different type of for a TTL game, you will find ki when we read about the circuit inside internal, see I can't be very sure of no, that it will give 5 volt. Okay, depending on how many gates is driving, how many gates, how many input signals you have. So this output voltage can differ a little bit. Okay, that doesn't happen in a CMOS logic, but TTL logic and all BJT circuits. Okay, so the output can be anything between 2.4 to 5. It's not with the noise. There is a drawback in the very functioning of these gates. Okay, so that drawback is not there in CMOS logic. Okay, so it is nothing to do with noise. Okay, it is inbuilt. It has got a limitation. That circuit has got a limitation. So when we learn about the circuit, it will be very clear, right? Presently, because you have not done, I have not covered these digital logic families. I will cover it towards the end of the class. Okay. Okay. Hmm. No, suppose you are giving an 1 volt input, okay, right? Instead of what happens if you are giving an input voltage of 1 volt to this gate, okay, it may not really give you the desired output. The manufacturer says, ki, okay, if it's an inverter, if you give 1 volt input for my 5 volt system, I will not assure you it will be one or zero. It can output could be anything, right? Yeah, correct, correct. That's what. Even if I give say 0.799 volt, right, within the blue band, okay, then output will be it could be zero also, it could be five also, right, or anything between the blue band. Okay, so all the best. Next we meet on Thursday, and lab students, and also probably I'll meet on Thursday. So I'll upload this PDF on the no, Google in the link which I have provided you, in the study materials, and I'll also upload the video also. Okay, in the video link which I have provided to you all. Okay, thanks a lot. Bye.